Thank you all for attending this last talk. I'm going to present a technique to isolate errors that are caused by hardware faults in distributed systems. So if a hardware fault occurs in a distributed system, it can crash a process, as we have seen in a previous talk, but it can also corrupt data. And this error might propagate throughout the system and cause severe outages. For example, in 2008, Amazon S3 service suffered a single hardware fault that became a bit flip, and this bit flip propagated via messages throughout the system and disrupted the complete S3 service, causing an outage of 8 hours and affecting also multiple users. Hardware faults are not uncommon in large-scale systems. So last year in VLDB, Google has presented their Mesa data warehouse system, which is used to store business-critical data such as ad clicks. And this system, the Mesa system, is designed from ground up to cope with data corruptions, because such data corruptions occur often in their environments. And interesting here is that in commodity hardware data centers, it is not sufficient to use standard techniques such as CRC in the messages and ECC in the memory modules, because these CPUs, the commodity CPUs used, can also fail. So how can a data corruption become a service disruption? In a distributed system, we have processes taking actions based on input from other processes. And once a fault occurs, typically the mindset that we have when designing fault-tolerant systems is that the process that is faulty is not going to take any actions anymore, it's just going to crash, it's going to die, and doesn't send any messages, so it's easy to reason about what is going to happen, because the correct processes are not going to take any actions based on input from the faulty process anymore. But once a hardware fault occurs and corrupts data, the faulty process actually behaves much more like a zombie. It still does things, but it does bad things. And it still computes on its data, but it computes incorrectly. And now, the worst thing a zombie can do, as you may know, is to bite other processes. Because once a zombie bites, the other processes becomes also a zombie. And this error propagation chain is problematic because we have now processes that could be correct, that were correct, they didn't suffer any fault, but they are behaving incorrectly because they computed on some input from a corrupted process. So this talk, this is very important. Here it doesn't help us to have ECC if the fault would occur after you load the data inside the CPU. And it wouldn't help us to have CRC in the messages if a fault occurs before the CRC is computed. And this is the case when a fault would occur inside the CPU, for example. So this talk is about how to isolate zombies from correct processes. So what we want to do here is not to kill zombie processes, not to stop them. We just want to isolate these processes from correct processes, in the following sense that once a correct process is receive a message from a zombie process that is corrupt, it is able somehow to identify that this message is corrupt, and it's able to drop that message. And in this way, it doesn't change its state in an incorrect way. And we call this property error isolation. So in this talk, I'm going to present a technique to implement error isolation, which is lightweight because it doesn't introduce memory overhead. It supports multi-threaded applications. And important is that it also allows us to use existing implementations of crash fault-tolerant systems and harden them to make them also tolerant against data corruptions. So how can we deal with data corruptions? We could take the same approach as the Mesa engineers, and we could look inside the code and decide where to add checks, add assertions to capture all the errors and misbehaviors that the code could have once a hardware fault occurs. But of course, this would be very complex and time-consuming, and we would need to have a very good team of engineers to know exactly which errors to cope with and when the coverage that we want to achieve is actually achieved. The problem here is that we don't have any guideline to decide where to add these checks. So another approach would be a principal approach, Byzantine fault tolerance. Here you take the service, doesn't matter what the service is, and you replicate it. And now it is easy to the client to filter out the corrupt messages. It can simply compare it with messages from the other replicas. The problem with this approach is however, that it introduces replication. And in many applications, you don't want to have replication. For example, if you have a memcached sitting in front of a database, this memcached is typically not replicated to achieve fault tolerance. So BFT would be an expensive solution for such application. A more promising approach would be what we call local hardening. This doesn't change the protocol like BFT would change, but it instead changes the processes of the distributed system in such a way that they compute and they check themselves. One of such approaches would be Swift, which is a compiler-based technique, and you compile the processes with this technique, but it's not developed for distributed systems and doesn't provide the property we're looking for. Another approach would be PASC, which was presented some years ago, and it provides error isolation, but it introduces a very high memory overhead, and it does not support multi-threading. So in this work, we are proposing a new approach, which we call scalable error isolation. Scalable error isolation is a local hardening, as I said, because we don't require the protocol to exchange more messages or add new steps to the protocol. We basically add redundancy to the processes of the distributed system in space and time. So space redundancy means that we have now state and redundant state, and if a fault corrupts the state, we can detect that with this redundant state. And time redundancy means that we re-execute parts of the code, and with that we can cope with faults, for example, corrupting some bits while the arithmetic logic unit is computing something. Our approach, say, is also end-to-end, because we require messages to carry a CRC, and the CRC is extended to protect not only the communication, but it also protects the computation. This means that once a process receives a message with a CRC, it checks the CRC, and if you both match, it knows that the communication was performed correctly, as usual, but it also knows that the computation of the sender process did not corrupt the message. So the last interesting property here is that say has also formal guarantees. This means that we have a fault model, we have a specification of our algorithm and some correctness proofs. And if you would employ say in your system, you would be inheriting these properties too. We call say a scalable error isolation because we scale in different dimensions. First, we don't introduce much memory overhead. Actually, if you have ECC in your memory already, in your CPU, in your memory modules, we don't introduce any memory overhead. Say also support multi-threaded applications. So this is important nowadays when we have multi-core processors and many applications are multi-threaded. And say also allows us to use existing implementations. So you can take a code that is already existing there and you can harden afterwards. So you can first design the system to cope with crashes, and afterwards you apply the technique to cope with data corruption. So the remainder of this talk is organized as follows. I'm going to give you an overview of say, not many details. You can look in the paper and in the technical report for the more details. I'm going to give you also some information about one of the challenges we had to deal with to support multi-threaded applications. I'll also talk about our implementation, which is called libsay. And finally, I'm going to highlight some of our experiments in our evaluation. Okay, so let's start with our requirements, the fault model and the algorithm. The only real requirement we have on applications to use say is that they are event-based message passing. This means that they receive messages, there is an event handling phase occurring which changes some state, and then there are messages being produced. And this is what an event handler does. And if you have multi-threaded applications, we require also all shared variables to be protected and accessed only in critical sections. And these critical sections are protected by locks, and we assume that these locks are going to be acquired in a consistent order to avoid deadlocks. Given these requirements, we have then a fault model that is very general. We model hardware faults as arbitrary state corruptions. This means that in the execution of a process, if a hardware fault occurs, it is an ask fault, meaning that it can change as many variables as it wants from the state, simply corrupt potentially all the variables of the state of the process. And afterwards, the instructions continue being executed from the process. Now, if it's an arbitrary state corruption, it could generate any Byzantine behavior. So we restrict the asked faults with a set of assumptions that we believe to be realistic. First, we have a fault frequency assumption. You can have as many faults as you want in one execution, but we assume that within one event handler, we can have at most one fault. This fault can still corrupt as many variables as it wants, as long as the second assumption holds, which we call corruption coverage. Corruption coverage means that you have state and you have redundant state, and if the fault corrupts both, you can detect it. In other words, it means that if you have error detection codes in place, they work. Now the algorithm is a two-step algorithm. There is first a transformation of the existing system, and then in runtime the algorithm performs several additional steps. The transformation takes every event handler of the processes of the distributed system and expands them in multiple phases. And these phases then in runtime work as follows. The first phase checks that the input message that is arriving to be processed matches the CRC. And if it doesn't match the CRC, the message is going to be simply dropped. Then the next phase executes the event handler for the first time. Here, whenever we read something from the state, we compare it against the redundant state, and if it doesn't match, we crash the process. This could occur, for example, if a fault occurs here before the check and corrupts the variable we are going to read. Then the check would detect that, and we would crash. But if the fault occurs after the check, then we cannot detect that, and we might propagate this to other variables via computation. To detect this sort of fault, we re-execute the event handler. To be able to re-execute the event handler, we snapshot all the variables that we modify, and we save the old values in buffers. Then we reset the state by writing back the new old values in the state and writing the new values in a buffer. We re-execute everything, and then we compare the updates from the first execution with the updates from the second execution. And here, if both executions produce the same output, same state updates, then we are fine, we can send messages out. Otherwise, there was something that happened, some fault that happened in the execution, and the process crashes. It could still occur that a fault, for example, corrupts the program counter and brings the execution of the process to the instruction just after the validation, so that you jump the validation due to this fault. In this case, we cannot stop the process from sending a message. The process could still send garbage out. But that's fine with our approach because, as I said before, we require messages to carry a CRC. And if the process sends a message with a CRC, this CRC is not going to match the message because the CRC is calculated only in the second execution of the handler. And if the first execution is skipped or the second execution is skipped, the payload and the CRC of the messages are not going to match. And in this way, if some garbage is sent out, a receiver can compare the message and the CRC and can see that they are corrupt and can drop the message. And in this way, we guarantee error isolation. So now I'm going to give some details about one of the challenges we had to deal with while supporting multi-threaded applications. So as you can imagine, we re-execute the event handlers, so they have to read the same values from the memory in both executions, so they have to be deterministic. But if we have multiple threads sharing variables, then a thread 1 could, for example, read a value A, and then a thread 2 could interleave with this thread, overwrite that value with a B, and then in the second execution in thread 1, it would read another value B, and now it would crash in the validation, although no fault actually happened. To cope with that, what we do is to employ a two-phase locking algorithm. So we acquire the locks in the first execution, but we don't release them. We just release them after the validation has been finished. In this way, we isolate threads that are conflicting. And then we can send the message and we can re-execute the event handler deterministically. But we don't require here a deterministic scheduling. Our implementation is called libc. This is an implementation in C, and it also targets C applications. And to explain the implementation, I have here a small server code that reads some message from the network, does something with the message, changing some state, updating some table or something like that, then creates some output message, and then sends this output message out. To employ our system, to harden some system with libc, what one developer has to do is to mark the event handler with a begin and an end marker. So he has to mark where the event handler begins and when it ends, and the event handler is basically everything that changes state. The begin also compares the message with the CRC, and if it doesn't match, discards the message. The second step of what the developer has to do is to annotate the output messages. This is done with output append and output done. This annotation is necessary to tell our library which pointers belong to messages, and then our library computes CRCs in the background. And finally, the developer has to use the CRCs that we calculate in our library. So once you send a message out, you retrieve the CRC from our library to send with the message. Now, once this annotation is done, this is basically what the developer has to do, and it can run a stock GCC compiler starting from version 4.7, and all the state updates that occur between begin and end will be instrumented and redirected to our library. So the method called do something here could be arbitrarily complex. You could have multiple functions, and the compiler is going to instrument all the state updates and redirect that to our library. And this is done using the transaction memory pass of GCC. Here it is important to note that we don't have a transaction memory implementation, but we use this interface to capture the writes that are done to the memory. And then in runtime, libc is going to do the rest for you. It's going to re-execute the code twice, so the event handler twice. The first time that end is met, there is a set jump long jump scheme that brings you back to the begin. Then the event handler is executed again. There will be CRCs calculated, and finally, once the end is met again, the validation occurs, comparing the updates from the first execution with the updates from the second execution. Important here is to note is that no code outside the begin and the end are going to be instrumented. So the stack, the network stack or other code that is outside of this event handler is not going to be modified by the compiler. Now I'm going to give you some details about our evaluation. We have performed a fault coverage evaluation and a performance overhead evaluation. And for that we have used two applications. First is memcached, which is a key value store that is widely used for, as a cache for databases. And internally is just a huge hash table with some eviction queues, and it's multi-threaded. The second application we have used is Deadwood, but I'm not going to talk about this application in this talk. You can take a look in the paper if you're interested. Our fault coverage was divided in two parts. First, we have done software fault injection, and then we have done hardware fault injection. In the software fault injection, we try to see how well our library is detecting data corruption. And for that, we have run memcached and randomly selected instructions and corrupted the operands of these instructions with a binary instrumentation tool, PIN. And the faults that we generated fall mainly in two categories. Control flow faults, which corrupt the program counter, and data flow faults, which corrupt operands of, for example, an addition. And what you can see in this table are the undetected errors, here marked. These are errors that propagate until the messages. So these are the errors that became visible externally from memcached. And for the data flow native memcached, you can see that up to 44% of the errors corrupted messages and could perhaps disrupt the distributed system. And with our approach, we could reduce that by 2 orders of magnitude. Similarly for control flow faults, but control flow faults are slightly less dangerous because they usually result in a crash of the process because they bring usually the process to execute some invalid instruction. So the takeaway of this experiment is that with SAY, we can reduce 2 orders of magnitude the undetected errors. We have then performed hardware fault injection. Our goal was to see what happens with our library if real faults are injected in the system. And then we ran a memcached in the same way. And we can see that the great majority of errors that were injected with our approach resulted in detected errors. Just some details here for our fault injection. We have performed undervolting. So we have an AMD bulldozer processor where we fix the frequency of the processor and we lower the voltage of the processor, bringing it to an unstable state. The important result of this experiment was that by doing this real fault injection, we could see messages being created with incorrect content if we don't harden the library, if we don't harden the memcached. But if we harden it with libc, we don't see any errors. And finally, our performance evaluation was done with memcached 2. And here we have varied the number of threads and the probability that the threads conflict in the table. For that, we have basically, on the left-hand side, you can see the number of threads that increase. And we have about 20% overhead with small message sizes. This 20% overhead depends on how much code you have inside the event handlers and how much code is outside of the event handlers. And if you increase the message sizes, this starts getting less, and at some point you don't see any overhead anymore. One important limitation of our approach is that if you have too much conflicts between the threads, so if the threads are trying to acquire the same locks, then the performance might decrease drastically because you have longer critical sections due to the re-execution of the event handler. So the takeaway here is that if you have enough cycles, spare cycles, and if you have enough parallelism, then it can occur that you have a negligible overhead with our library. So what I have presented to you is an algorithm to isolate errors that are caused by hardware faults in distributed systems. This is a local algorithm that doesn't change your underlying algorithm. It is end-to-end. It's effective against data corruptions. And we have a library that is open source. You can try it yourself. It doesn't introduce any memory overhead if you have already ECC in your computers. And introduce little performance overhead if you have non-intensive applications, CPU applications. Okay, thank you for attending this talk, and I'm open for questions.
Hi, I'm Edward from Cornell, and it just occurred to me that we saw an earlier talk at this conference about how sometimes network protocols will deviate from the specification specifically in not returning an explicit error code when a client sends a malformed request, but simply dropping the packet, and this causes the client to continue trying to send requests. So are you intending this to be used only internally, or have you considered what will happen if applying this library makes the external facing parts of the protocol no longer return an explicit error when they should be? Because your reaction is, if you see a malformed request, to always drop the packet, to just discard it instead of generating an error. So
you have options how to handle it in different ways. So if you see in our example code, if you have a message that doesn't match, you can handle it in different ways by, instead of saying there in the else a continue, you can perhaps send a message back to the client. Does this answer your question?
Okay, yeah. If this is not something that you inject, this is something the developer gets to write and could choose to
right.
say.
So this is not a completely automated approach. So we basically automate the process of instrumenting all state updates with this transaction memory pass, but part of the work still has to be done by the developer.
Okay, that makes sense.
Yes.
Hi, Sergei from Stanford. Are there cases where faults generate errors in libc itself that then won't be verified? And if so, would you be able to shed some light on what those might be? So
there are faults that can occur. So we care about the faults that occur in the library itself. And in our model and in our proof, we can show that we can capture those too. So given the assumptions we have that there is a single fault that can occur in one execution of an event handler, we can capture the faults that occur inside the library too.
Okay, so I'm thinking of a case where somewhere between, say, the first time you do the check and the second time you do the check, you have some like jump inserted that jumps right at the correct spot so that you get so far into the first check that the second check will succeed, but not so far that the second check won't fail, if that makes sense. So those cases aren't possible where you jump, where you do a branch so that you don't, so that the verification succeeds, but the fault doesn't get catched by the verification. Sorry, that was convoluted. So I guess my question is, so you're saying there does not exist a case where a fault in libc results in correct verification or a false positive verification?
So the short answer is we cope with the faults that occur also in libc,
Okay.
given our fault model.
Okay. Thanks.
Well, let's thank the speaker.